Anytime.
Great. So hi, so I'm Andy Mensky. It's a pleasure to have the opportunity to speak at this school. So what I'm going to discuss, at least today, is sort of a worked example of what Maxime discussed in the morning. So it's going to be about counts of special trajectories of quadratic differentials. So this will be defined momentarily if you don't already know what they are. But I guess at least some subset of people here are from the flat surfaces community, and for them these should be very natural objects. So what I want to explain is that these objects, which are sort of reasonably concrete things, are actually examples of the story that Maxime told. So the story is going to be that these are examples of dt Donaldson-Thomas invariants. Maybe they should be called generalized Donaldson-Thomas invariants, but I guess these days we just call them Donaldson-Thomas invariants. Anyway, in the sense of Maxime's talk, this morning. And so that alone is kind of interesting. So they're sort of a nice computable example in that theory. So if you were interested in Donaldson-Thomas invariants for their own sake, you might like this because it would give you something that you could really get your hands on. But as it's turned out, embedding them into this context, so once you start thinking about these trajectories and thinking about them as examples of Donaldson-Thomas invariants, that turned out to embed them into somehow a bigger story that I want to try to sketch out at least a little bit. So embedding these trajectories, embedding them in this context. So this is just some puffery, but it's puffery to kind of set the stage. So it has led to other developments, which you can understand even if you don't understand generalized Donaldson-Thomas invariants. Well, the first is that they obey the wall crossing formula of Kinsevich and Soibelman. So I'll describe how that wall crossing formula operates in this particular context. And that's something you can understand even without knowing what a Donaldson-Thomas invariant is. But as it turns out, they also play a role in a lot of other constructions. So one thing is that they're important ingredients in studying the asymptotics of differential equations. What goes under the name of the WKB approximation. They're also important ingredients in a new construction of Ricci flat metrics. In fact, hyperkähler metrics. So these are some new things that you can do with quadratic differentials once you understand this perspective on quadratic differentials. Another thing, which I think ought to be of particular interest, and which you can understand without understanding this stuff, is that it seems that the trajectories of quadratic differentials are actually just the first example of a sort of tower of things. So I'll put a star on this one. So these things admit a natural generalization. To what I'll call higher rank invariants. So the trajectories of quadratic differentials are you have some curve and you're studying literally just some paths on that curve obeying a differential equation. These higher rank invariants are similar things. Again, you start with a curve, but now you don't just start with a quadratic differential. You start with a quadratic differential, cubic differential, quartic differential, some finite collection of differentials from order degree 2 up to k. And given all that data, you define some higher rank invariants which are counting not just trajectories, but in general they're counting some networks of trajectories. And then, so this is one of the main things I want to get to. And this generalization is something that's much easier to see once you understand about the wall crossing formula. And then the last thing, which I may or may not get to, is that the real reason why I and my collaborators, I should say that most of what I say here is going to be, so most of what I say is joint work with Davide Gardotto and Greg Moore. So we actually come from the physics community, and most of this stuff really arose from, not from thinking about quadratic differentials sort of in isolation, but from embedding them into physics, into the physics of supersymmetric quantum field theory. So if people are interested in that, I may say something about that in the last lecture. So this stuff came from physics. So what I want to do is to try to describe all of this stuff from a kind of unified perspective. And this perspective is actually work in progress with Gardotto and Moore, and so it's I think a big improvement over how we thought about these things before. But on the other hand, because it's in progress, some details can still be wrong. So there's the possibility of some sign errors and so on as we go on. Fortunately, the basic picture is by now quite clear. So I hope you'll forgive me. Okay, great. So what are we going to do? So this will be quite familiar to those who know about quadratic differentials. I'm going to start by defining something I call S-walls. So let's fix a compact complex curve C. Let's see. So we're going to do something involving quadratic differentials. What's a quadratic differential? So I'll denote my quadratic differentials by phi 2. So it's some object that lives on the curve. It's locally just given by a function on the curve, but globally it's multiplied by dz squared. So this is, if you like, phi 2 is a section of the square. To be fancy, it's the square of the canonical bundle of C. But it just means this. So suppose I have such a thing. For a minute, let me not specify whether it's holomorphic or meromorphic. In a little while, we're going to consider ones which have poles. So the thing won't be globally holomorphic; it will have some poles. But for a few minutes, at least, what I say is going to be independent of that. So suppose I have one of these quadratic differentials. So any such phi 2 determines determines a foliation of the curve. In fact, not just one foliation, but a circle's worth of foliations. So it's a one-parameter family of foliations. Okay, honestly, they're singular foliations. We'll see where the singularities are in a second. So I'm going to call my foliation f of theta, this is bar theta, f of theta and phi 2 of the curve C. So what is this foliation? Well, to tell you the foliation, I just tell you what its leaves are. Where's the eraser now? So this parameter theta, I would change my notation if I weren't afraid of getting confused. So this parameter theta plays the same role as the parameter that was called phi in Maxime's phi. So it's somehow, we have things that have a phase, and theta is going to be that phase. So the leaves of f of theta phi, or sometimes called the trajectories of this quadratic differential, I might sometimes use that word. So they're just paths in C, along which e to the I theta, e to minus I theta, e to the minus I theta square root of phi 2 is a real one form. What does this mean? So phi 2 is some global thing. It might not have a global square root, but locally it has two square roots. So just choose locally one of those square roots. Multiply it by, so phi 2 was a quadratic differential, so its square root is a one form, a locally defined one form. Multiply that locally defined one form by e to the minus I theta, and then restrict it to some path. It might or might not be real. If that one form is real, then that's one of the leaves of this foliation. So fortunately, the condition of it being real doesn't depend on which square root I took, because changing the square root just changes the thing by a sign. So even though this thing is locally defined, the foliation is globally defined. It's not globally oriented, but it's globally defined. So if you like, another way of thinking about this foliation would be in local coordinates, we could just write phi 2. So you could choose a local coordinate where phi 2 is literally dw squared. Then these leaves are just straight lines with angle straight lines in W. Okay, so for those who think about flat surfaces, this phi 2 also determines a flat metric. Sorry, I'll say that in 1 second. So where is this foliation singular? This foliation is singular at the zeros of phi 2 and at the poles if it has poles. But even if phi 2 doesn't have poles, this foliation is singular at the zeros of phi 2. So. And what does the trajectory structure look like around the zeros? Well, assuming they're simple zeros, and from now on I'll usually assume that my quadratic differential only has simple zeros. So that means I'm avoiding some complex codimension 1 locus in the space of quadratic differentials. So assuming that the zeros are simple, then the local structure looks like, so we've got the zero, let's see, color for that, okay. So the zeros of this quadratic differential red crosses. So the local structure of this foliation around the zero is that it has kind of 3 prongs coming out, and then the rest of the leaves go like this. So we've got a foliation of our curve that has singularities like that. And then, so another way of thinking about it is that this phi 2 also determines a flat metric on the curve, a flat metric on the complement of these singularities. Of course, the curve has some genes. It couldn't have a flat metric globally, but it can have a flat metric on the complement of these singularities. And then these leaves that we're drawing are just the geodesics in that flat metric. In fact, for any theta, so you have geodesics with all possible angles. So for any theta, the leaves of this thing are geodesics. And by fixing theta, we're picking up some particular geodesics. Okay. So that's okay. So those are the trajectories of the quadratic differential. There's no reason not to use this middle board. Those are the trajectories of a quadratic differential. Now we're interested in some special ones. So, well, in fact, in almost everything I'm going to say, I'm actually not going to use the sort of generic trajectories of the quadratic differential. I'm only going to use the special ones. The separating trajectories, which are the ones that come out of the ones that are coming out of the zeros. These zeros sometimes you call turning points. I might sometimes say turning points. So let's try making those brown. So I'm going to call the trajectories emerging from zeros of phi 2. Well, you might call them separating trajectories. I'm going to call them S-walls. Okay, so that's something you can do with a quadratic differential. Now, what are our Donaldson-Thomas invariants going to be? Well, of course, a generic S-wall, if I pick some sort of random value of theta, and I look at all the S-walls on my curve, what generally happens is that they come out of this 0, and then they just run around the surface forever, or if there's punctures, maybe they run down to the, they're sort of asymptotically ending on the punctures, the places where this quadratic differential has a pole. What they don't generally do is run into another 0. But on the other hand, for some special values of theta, it may happen. So for special values of theta, so non-generic values of theta, so we may have S-walls that have both ends on zeros of phi 2. And there's sort of two distinct ways that this can happen. There's two distinct ways that it can happen. One would be that you have two distinct zeros, and you just have a trajectory that goes from one to the other, and then so each of these has three things coming out of it. So two of them are going in some random direction, and then but one of them is actually connecting one zero to the other. So this we call a saddle connection. And the other possibility is that you have a single 0, and it has one trajectory coming out like this, and then another one that actually comes back to itself like that. So this curve has some topology. So there's some topology of the curve contained in here are some poles of the quadratic differential that allows it to do this. So this is a closed trajectory. And so these are the things that we're going to count. These are the analogs of the special Lagrangian submanifolds that Maxime was talking about in the Calabi-Yau threefold. Here we're just on a curve, but nevertheless, this is to be thought of as the case n equals 3 of Maxime's story, not the case n equals 1. So these objects are analogs. In fact, the analogy can be made sharp, but let me not try to say it right now. So these are analogs of the special Lagrangian 3 cycles in Maxime's talk.
Actually, they're not analogies, these are special Lagrangian 3 cycles for local Calabi-Yau.
Right, exactly. So it's not just an analogy. There is actually a Calabi-Yau threefold you can make such that these things are literally, so the Calabi-Yau threefold is kind of fibered over some curve, and you literally have a 3 cycle which is fibered over this trajectory. So it's roughly, you have a sphere that's fibered over this thing and collapses at the two ends. So here it makes a 3 sphere. In this case, it actually makes an S2 times S1.
But this is exceptional, as you said.
Sorry?
This is exceptional situation that we have these things.
It's exceptional if I fix the value of theta. Then I generically don't expect this. But on the other hand, you can ask the question, suppose I fix my quadratic differential but I don't fix theta. I allow theta to vary through the whole circle of values. In that case, this is kind of a codimension 1 phenomenon, right? Because it's a shooting problem. I shoot this thing out and I look where it goes. So sort of in codimension 1, you expect that it would hit another thing. So they're not generic once you allow theta to go through a whole circle. Sorry, they are generic once you allow theta to go through a whole circle. And what we're going to count is those numbers. So let me say that more precisely. So I want to define these integers. I want to define the integers omega of gamma. So far I haven't told you even what gamma is. So the question, our interest is in this question, how many, so I'll call these things collectively special trajectories. trajectories. And the question is, how many special traj occur in the family? Let's write it this way: f of theta phi 2, while theta runs through the whole circle. Okay, so the first simple observation is that these special trajectories, there may be a lot of them, there may be infinitely many of them, but there's only countably many of them. Why is that? So they occur only at countably many theta, and the proof of this will give us some hint of how to sort of organize these objects. So why? So we've got this quadratic differential phi 2, and phi 2 determines, very canonically, a double cover of C, which will play an important role in everything else we do. So I could call it sigma of phi 2, and it's if you like the Riemann surface for the square root of phi 2, right? So I said that phi 2 doesn't have a global square root. So we can make a Riemann surface whose sheets are just the choices of square root. The choices of square root of phi 2. So the points of the thing are just solutions of this equation. And so because phi 2 was a quadratic differential, its square roots are one form, so this double cover is sort of naturally sitting inside the cotangent bundle of the curve. And now, so each of the special trajectories, so you think of them as living on C, but they actually sort of naturally lift to things that live on this double cover. So it lifts in a canonical way and moreover, they're kind of open things on C, but they lift to closed one cycles on sigma of phi 2. Well, maybe it's easiest to explain that just by drawing a picture. So for example, if I have one of these special trajectories, so that's living on C. And I can give myself quite enough room here. I'll redraw. Let's do it over here. So I have one of these special trajectories living on C. Special trajectory on C. So on the double cover, so the double cover has two sheets. But it's a branch double cover, and the branch locus is exactly the zeros of the quadratic differential. So I'll draw a picture. Oops, a picture. It sort of looks like this. These are the pre-images of the branch points. And now, so I take this curve. If I lift it up, I just take the pre-image of that thing upstairs on sigma, but I'll take both of its pre-images, and I'll take them with opposite orientations. In fact, there's a way of canonically determining the orientation, but let me not get into it. I take them with opposite orientations, so then I get a closed curve up here. And so there's a little bit of topology that kind of labels this special trajectory. So it gives in particular, so that determines a class gamma in the first homology of this sigma. So now, what do I want to say about that? Well, so now we can define a number.
Wait, upstairs, the foliation of singularities as you draw?
So let's see, now I'm not drawing the whole foliation, I'm just drawing the
and then you can lift the foliation.
Then I could lift the whole foliation if I wanted
to. So what does it look like at the pre-image of the branch point?
At the pre-image of the branch points, it has 6 things coming in. Yeah.
And by 2, then
That's right. So, there's 3 here, and each one of them just has 2 pre-images, so it becomes 6 things. That's right. Okay, so I'm in the middle of explaining how we should classify these things. So they have a homology class, and now
Also, maybe you can put it's anti-invariant and in evolution.
That's true. That's an extra fact about this homology class. Yeah. So that's true. So you can say more. It's not only in the first homology, but it's actually in the part of the first homology that's anti-invariant under the involution. So there's an obvious involution that just exchanges the two sheets of this thing. Right. And I'm going to use the name, let's see, this lattice will be convenient to call it capital gamma. I could have also called this capital gamma. I'm hopeful that it won't make too much difference which one I call capital gamma. But this gamma is supposed to be the analog now of the gamma that appeared in Maxime stuff. So we're going to mostly have the same notation. So let's call gamma. So each of these special trajectories has a gamma, and I'll call it the charge of the trajectory. Okay. So now for any gamma, whether or not it was the lift of some trajectory, we can define this quantity z gamma, which is just the period. So we've got a one cycle on sigma, and now we can take the period of what's lambda. Lambda is just the tautological one form. So this thing is sitting inside the cotangent bundle. So it has a sort of tautological one form on it. And now, exactly because of the differential equation that defined these trajectories, so if gamma is the lift of a special trajectory, is the charge of a special trajectory, I guess I should say, that's what I'm calling it. If gamma is the charge of a special trajectory, then this z gamma, well, you're integrating this one form, but this one form actually has constant phase along the trajectory. That was more or less the definition of the trajectory. And so you get z gamma is in e to the I theta. If I've chosen my orientation correctly on this thing, it's in e to the I theta times the negative middle number. And in particular, okay, so now we've got these numbers, we've got this collection of numbers z gamma, right? This collection of numbers z gamma labeled by the homology classes in sigma, and there's only countably many z gammas, so only countably many gamma and gamma. So this can be satisfied at most for countably many thetas. So that's the simple thing I was trying to say before. Star occurs at most for countably many thetas. And moreover, once you fix your gamma, once you fix the charge you're looking for, then theta is determined. You know just where to look for it. You know which foliation to look at. Okay. So the proof of this already kind of suggests that these z gammas are a useful thing to look at. And that's what we're going to see as we go on. Okay, so now I want to talk about, I want to define the actual invariance. But I have to do a sort of unpleasant technical thing, something I don't like to do, which is I have to sort of restrict the generality of this story. So the sort of most interesting version of the story would actually be the story where phi 2 is an honest-to-God holomorphic quadratic differential with no poles or anything. Now, everything I say, and even the arguments I give, are mostly not going to depend on whether the thing has poles or not. But for safety, there will be occasional moments where things will look much clearer if I put in some poles. So for safety, I'm going to assume now that the thing has poles. So you should think of this as some technical thing which you would like to not do. But let's do it. So let's fix some mark points. So z1 up to zn on C, which I'll sometimes fall into the habit of calling punctures. And so we'll only consider phi 2 which are meromorphic, not holomorphic, and with double poles at all of the z-i's. So yeah, this will be to simplify the arguments, but also the sort of simplest explicit examples, the ones you can actually access, are ones that have punctures. So in this case, my sigma, this sigma now is also going to have punctures. So I just delete the preimages of the punctures, the poles of phi 2. So think of sigma as being this non-compact curve. We don't compact phi. Okay. So now I want to define these Donaldson-Thomas invariants. Well, as with Maxime's story, I don't want to try to define them for a generic quadratic differential, even a generic quadratic differential with this property. I want to define them, I don't want to define them for an arbitrary quadratic differential, even one with that property. I want to define them for quadratic differentials which are in some sense generic. And what I'm going to mean by generic, DC invariants. So take phi 2 generic. And what it's going to mean is that all of the z gamma are linearly independent over R. So, you know, the z gammas, well, sorry, this is a bad way of saying it because, of course, z2 gamma is never linearly independent of z gamma. But what I mean is that, if the z gammas are linearly dependent, then the gammas themselves are also linearly dependent.
Not pairwise independent.
Pairwise, let's see. Let me try something and see if it works. If sum of n gamma, if sum of c gamma z gamma equals 0 for all c gamma real, that implies.
No. It's wrong here because you get 3 vectors in R. They're always linear dependent with real coefficients. I think.
Yeah. Okay. Fine. So.
I think it's exactly the same conditions. That non-proportional vectors go to non-proportional.
Yeah. All right. Let's just say it that way. Right. So. Z gamma over z gamma prime is real if and only if gamma is proportional to gamma prime. That's good. So let me assume that I'm in that. Let me assume that I'm in that generic situation. So that's some condition on phi 2. And in that case, the possible phenomena that can happen in this foliation are pretty limited.
I'm sorry, I'm confused. Is it real or positive real?
It doesn't matter because
so it doesn't matter. Yeah. Okay. It's somehow more canonical to think of it as being R plus, but the condition was the same whether or not it was. But you're right. It's sort of morally better to say R plus. So then, the possible phenomena f of theta phi are pretty limited. One thing you can have is you can either have an isolated saddle connection. So one thing you can have is just one saddle connection. And the other thing you can have is you can have closed trajectories. Now in that case you don't get just one. So you can have a closed trajectory. So I defined my closed trajectory to be one. Oh, I've reversed my color. All right, for a minute the colors have reversed. So I defined, when I said closed trajectory, I had what might seem like a funny definition. It had to be an S-wall, meaning that it had to have one end, and therefore 2 ends, on these zeros. So if you have one of those, you also get another one like this. And then in between, there's actually a family of, there's a one-parameter family of closed geodesics. And by putting this genericity condition, I've forbidden other funny things from happening, like you can have a family of closed trajectories where the boundary actually is made up of several saddle connections connected to each other. By putting this condition, the only things that can happen are you can either have a single isolated saddle connection, or you can have a family of closed geodesics.
In fact, it could be of two types, because you can have also a semi-infinite tube.
Oh, it could be ending on the puck shoot, that's true. So that's right. You can imagine having, if there's a pole in the middle of the thing, you can imagine having a tube like this. Yeah, this thing I'm not going to care about for a reason that I hopefully will explain. But that's right.
And you have only double poles, right?
I have only double poles.
Mm-hmm.
But it's true that this thing can happen. It can be
But
surrounded
what
by
are the
double.
singularities of double poles of the foliation?
Yeah, okay, good. So what does the foliation look like near the double poles? Let me say that just in 1 second. So first I want to say that if I have a single saddle connection carrying charge gamma, then I'm going to define omega of gamma is equal to 1. And if I have one of these families of closed geodesics, again with charge gamma here, then I'm going to define omega of gamma to be -2. This situation is a little bit special because this gamma would be sitting in the kernel of the intersection form. And in that case, I really don't care what its omega of gamma is. I could define it to be anything. So what the hell, just to be uniform, I guess the natural thing here would be to say omega of gamma equals -1. But I'm not going to care very much about it.
Understand your picture. Why do you have two closed circles now?
Why do I have two closed circles? Yeah, it's because, so if you look at, you assume the existence of one of them.